All right, let's jump right in. Today, we're talking about one of the coolest, most fascinating parts of AI, reinforcement learning. And what's so cool about it? Well, it's all about teaching machines not by giving them all the answers, but by letting them figure things out all on their own. So, let's start with a big question, right? How do you actually teach a machine a new trick? I mean, if you want it to master a super complex game, or say guide a robot through a messy room, where do you even begin? You can't possibly write down a rule for every single thing that could happen. There's just no way.
Well, here's the twist. You don't give it an answer key. Not at all. Instead, you train it. Kind of like how you'd train a dog. Seriously, you set up a system of rewards, like a treat for doing something good, and punishments, or penalties, for doing something bad. And suddenly, the machine's goal becomes incredibly simple. Get as many of those treats as possible.
And that brings us to the absolute star of our show, the reward-seeking agent. You're going to hear that word a lot. The agent is the part of the AI that's doing the learning, the one making all the decisions. It's basically dropped into a world, and its job is to figure out the rules of the game.
So let's be clear. The agent is our learner. It's the decision maker. Just picture it. It's the robot trying to find its way out of a maze, or it's the AI staring at a chessboard, trying to figure out the absolute best next move. It's constantly looking at its surroundings and then deciding, okay, what do I do now? And where does this agent live? Well, that's the environment. Think of it as the sandbox the agent gets to play in. It's everything outside of the agent itself. For a robot, it could be a real physical room. For a game AI, it's the digital world of the game, like the board in Go. It could even be a super complex simulation of the stock market for a trading AI. Okay, so the agent is in an environment. What does it do? It takes an action. An action is just any possible move the agent can make. It's a choice. Super simple, right? For our robot, the actions could be move forward, turn left, turn right. For an AI playing a video game, it might be jump, duck, or fire.
And now we get to the most important piece of the puzzle, the reward. This is the feedback. It's how the environment talks back to the agent. A positive reward, a +1, is basically a treat. It's the environment saying, yes, good job, do more of that. A negative reward, on the other hand, is a penalty. It's a clear signal saying, nope, bad idea, don't do that again.
So this all comes together in what we call the learning cycle. It's a simple loop, really. Step 1, the agent looks at its current situation. We call this its state. Step 2, based on what it knows, it picks an action. Step 3, the environment reacts, giving it a reward or a penalty, and showing it the new state. And step 4, the agent takes all that new information and uses it to update its strategy. Then, it just does it all over again, and again, and again. We're talking thousands, even millions of times. And with every single loop, it gets just a little bit smarter. But, it's not always that simple. The agent has a really tricky choice to make at every step. It has to decide, should I try something totally new, or should I just stick with the move I already know works pretty well? This is a classic problem, and it's called the explore versus exploit dilemma. The easiest way to think about this is with a restaurant analogy. Imagine it's Friday night. Do you go to your absolute favorite restaurant, the one where you know the food is going to be amazing? That's exploiting your current knowledge. Or do you take a chance on that brand new place that just opened up? It could be the best meal of your life, or it could be awful. That's exploring.
And this trade-off is absolutely fundamental to learning. When the agent explores, it's basically trying new, sometimes random things just to see what happens. The goal is to gather more information, to maybe stumble upon a gold mine, a strategy that gives a way bigger reward than anything it's seen before. But when it exploits, it's cashing in. It's using the best strategy it already knows to get the most reward it can right now.
So the real magic, the key to smart learning, is finding that perfect balance. You see, if the agent only ever exploits, it gets stuck in a rut. It might be doing okay, but it could be missing out on a much, much better way of doing things. But if it only ever explores, it just wanders around aimlessly, trying random stuff, without ever actually using the good information it's found to get rewards. It's a constant balancing act. Okay, so we've got the basics down. Agents, rewards, that whole explore-exploit thing. Now let's see how this all connects to the real world. Because this simple idea, well, it's the engine behind some of the most mind-blowing AI breakthroughs we've ever seen.
I know, it might sound almost too simple, right? Just trial and error, guided by rewards. But believe it or not, this is the very same principle that allows an AI to master incredibly complex tasks. We're talking about things like defeating the world's best human players at the game of Go, or teaching a robot arm to assemble a product with perfect precision.
And you know what? We actually interact with this stuff every single day. Think about the recommendation engine on something like Netflix or YouTube. It's not just trying to find one video you'll click on right now. No, it's playing the long game. It's using reinforcement learning to figure out which series of recommendations will maximize your total watch time over weeks or months, keeping you hooked. The same idea applies to advertising, where it can automatically shift money to the campaigns that are working best, all in real time.
Then you have autonomous systems, where this stuff is an absolute game changer. It's how a robot in a warehouse learns to pick up an object it's never seen before. It's a key part of how self-driving cars learn to deal with the chaos of an unpredictable city street. And of course, there's gaming. This is where RL really became famous. When DeepMind's AlphaGo beat the world Go champion, it wasn't just playing moves it had memorized. It was using reinforcement learning to invent completely new, creative strategies, moves that professional players had never even thought of in thousands of years of playing the game.
And its potential to optimize the world around us is just massive. Think about traffic control. Instead of dumb, fixed timers on traffic lights, you can have an RL agent watching the real-time flow of cars, dynamically changing the signals to bust up traffic jams and make everyone's commute smoother. It's also being used to make our energy grids more efficient. And, get this, even in healthcare, to help figure out personalized treatment plans, like finding the perfect dose of a drug for a specific patient by learning from their body's response.
So, where does all this leave us? What's next? Well, it's pretty clear that reinforcement learning is this incredibly powerful tool for solving a very specific kind of problem. Any problem that involves making a sequence of decisions in a really complex, messy environment.
And here's the most crucial takeaway from all of this. The bottom line is that reinforcement learning gives a machine a way to teach itself. All you have to do is define the goal, give it that reward signal, and the agent can automatically discover the best possible strategy to get there. It can figure out solutions to problems that are just way, way too complex for any human to ever program by hand.
And that really leaves us with one last big question to think about. If an AI can teach itself to win any game just through trial and error, what are the truly big, messy, important problems in our world that it's going to learn to solve next?